Great. So I think, we are in the golden age of AI, right? And what we are now seeing is increasing impact in so many domains. And to me, what's really exciting is the impact it's having on the sciences and in the area of scientific simulation, which has traditionally required large scale HPC and, what can AI provide there, right? What can we do better with AI? That's what I hope to give an overview today. And yeah, and that's, I think, the question, right? AI has been one of the most powerful technological forces we've seen. And it's mind-boggling how the complexity has grown over the last few years. If you count how larger the model has gotten, it has grown 30,000 times in the last 5 years, right? So we now have a new form of Moore's law, which is about AI complexity doubling every 2 months. So with this exciting scale, what is possible, right? I guess the largest developments have been in the language domain, but can we also have those developments in the sciences? Indeed, the AlphaFold is one of them, where scale has given us, right, the best model compared to any of the previous ones. The question is, can we do that also in other problems in sciences? And one important challenge with that is extrapolation, right? So going beyond what we've already seen or what the model is trained on, how well can it accomplish? And that's really important for the sciences. And indeed, I don't need to remind you that for this, we need both data and large-scale computing, right? The design of the algorithms is driven by also the availability of the data and the computing scale. And the question is, in the sciences, can we get large enough amounts of data? And this is a challenge, especially if the simulations are so expensive. Can we do it even larger than what the training data is, right? You may not be able to, for instance, simulate for a molecule of, say, size 100 or 1,000. So can you do it on smaller molecules and extrapolate? And that's what makes it different from standard supervised learning that we see in most of the standard AI problems. And that's where the other dimension of the scale comes in. On the HPC front, we have seen a lot of exciting gains in terms of our supercomputers getting more powerful, right, with each generation. But the difference is, unlike traditional HPC, which is involving 64-bit floating points, which is very high precision, AI requires much lower precision. And for that much lower precision, if we can do better, right, then we have a lot more flops available. And that's where now we are measuring the flops of our supercomputers in terms of the AI computations and no longer the traditional high precision computing. And so that's where we can now use the hardware much more efficiently than with traditional computing. And the question is, on top of it, can AI further enhance and give us orders of magnitude speed ups while retaining the accuracy of traditional simulations? And that's what I'm here to address, what would be the algorithmic developments needed to enable this. And just as a pointer to where we are in terms of the power needed in our supercomputers, right? We are now in the realm of exaflops, right? So the recently announced world's fastest supercomputer would have 20 exaflops of AI. And so we are getting now this large scale. And the question is, what is the right class of AI algorithms that could make an impact in challenging problems such as climate, weather, material sciences, and so on? And so this is where, for AI for science, right? How do we replace these traditional algorithms with uh, AI, hopefully, which can be much faster while retaining accuracy? The biggest challenge is that most of these phenomena are highly complex, multi-scale, and possibly chaotic, right? So meaning you have to really go to the fine scales to be able to learn this phenomena or understand this. With traditional methods, that's why these discretizations have to be at the fine scale. The question is, with enough training data, can AI learn this multi-scale phenomena without having to go to fine discretizations for solving each problem? And another aspect is also extrapolation in terms of the nature of training data, right? So if we can train only on small molecules and directly extrapolate to large molecules, then again, we can make this technique practical, because the traditional methods may be too slow, even on our world's fastest supercomputers, to be run on larger molecules. To give you an example, the fundamental equation that governs right, the properties of molecules is the Schrodinger's equation. So it's looking at the quantum level interactions between atoms in the molecule. And by current estimates, in order to compute this exactly on a molecule of size, say 100 atoms, it will take longer than the age of the universe on the current fastest supercomputers. So that's what we are talking about, this sheer importance of, or just infeasibility of being able to do brute force computations for getting some of these complex phenomena. And the question is, can AI make the right kind of approximations implicitly and be able to give reasonable answers to these challenging questions? So the first part of what I'll talk about is what we call neural operator learning, which is the result of having an interdisciplinary team come together, right, from applied math, material sciences, and AI, of course. And the question we asked was, we have partial differential equations. Can we use AI methods to solve them accurately? And indeed, to frame this problem, it appears to be a standard supervised learning problem, right? So the input is different examples of initial and boundary conditions, and the output are solutions to those given conditions, right? So if this is indeed the case, then we can use any standard neural network, train it, and that's that should work fine. So why is it more nuanced than that? So the difference is, unlike standard setups where we have a fixed sized input, right? So such as an image of fixed size or a vocabulary of fixed size, with the PDEs, what we have instead are functions, right? So it's a function to function mapping. So we should be able to solve the equation at any different discretization. So grids at different sizes, different kinds of right, shapes of grids here. So all this we should still be able to solve. And the traditional solvers can do that today, right? They can handle these different resolutions. And so now the question is, can we design AI methods that can do the same? And so that's why having a standard neural network is not good, because it is, for instance, the convolutional models are learning filters at a fixed resolution and don't easily generalize to another resolution. And the other difference we have to think about is, right, you're not just solving one instance of the problem, you're ultimately mapping functions to functions. And this is known as operator, meaning these inputs no longer are of finite dimension, but potentially infinite dimension, right? Because you can have like now the input as continuous within a defined domain. So given this, how do we now design methods that can handle changes in resolution and grid? And that was our motivation to go beyond. But again, the main intuition of where we start is like kind of asking, in a standard neural network, what we have is typically linear operations followed by nonlinearity, right? And these linear operations are of a fixed sized, say, matrix operation or convolution operation. So the question now is, how do we extend this to infinite dimensions? And the main principle here is, what does the solution of a linear partial differential equation look like? And what it looks like is a global convolution where you're integrating with this kernel, which is known as the Green's function, to give you an intuition. If it's a simple heat diffusion equation, the function would look something like that, right, in terms of how the heat propagates. So for simple linear partial differential equations, we can write this down as just a global convolution. But instead, for more general nonlinear PDEs, such as turbulent fluid flows, it won't be this simple. And so instead, what we do is define this neural operator as nonlinear compositions of such integral operators, right? So we compose this global convolution layers with nonlinearity. And by doing that, we can now approximate any general operator. And so then to make this tractable, what we do is to use the Fourier transform to solve this convolution efficiently. So meaning, instead of directly trying to learn that convolution, which is hard, we transform it into the Fourier domain, and then we learn the weights in the Fourier domain. So think of this as now we are filtering out frequencies in the Fourier domain and changing their weighting. And we also only filter out the low frequency modes in each step. But because we compose with nonlinearity, we can obtain the full nonlinear spectrum as well, or rather high frequency spectrum as well. And so a very simple approach that draws a lot of inspiration from classical methods that use the Fourier transform, but at the same time having the flexibility of representing any general operator and having the ability to learn this efficiently. And so the main intuition of why Fourier layers are much more effective than convolutional layers with learned filters is that they can capture global correlations much more effectively, right? Whereas the filters are small in standard convolutional neural networks. So that's one advantage. And the other is this ability to compute this global convolution efficiently, and having the property of handling different resolutions and grid sizes. And so that's the overall framework. And what's the outcome? What we can show is the ability to train on just low resolution data, right? So just say the 64 by 64 sized images and directly evaluate it on much higher resolutions. And so this is zero shot, right? So training time, we've never seen these higher resolution evolutions, but we are now able to also accurately resolve them. Whereas standard neural networks would not have this ability. And so that's the benefit of this principled approach, that we are resolution invariant. And by doing that, we can capture the underlying physics much more effectively. And this we can actually validate by looking at the frequency spectrum, right? The idea is if you only have low resolution data, we only see this part of the spectrum, right? This other part is never seen before. But still, this our model, the Fourier neural operator, is able to much more closely approximate it compared to, say, UNet. And so that's the benefit of having this framework that is able to handle different resolutions. And we see the benefit of this in many other applications, just to name a few. In the previous one, I forgot to mention the speed up we got was about 1,000 times. And that's because the solver, the traditional solver, is also GPU based and uses Fourier transform, right? So fast solvers exist for this case, and hence, we even then we get such a big speed up. And the main intuition of why is for these solvers, they still need to do fine discretization as they move forward in time. Whereas we can do much bigger gems using the machine learning method, right? We don't need that fine discretization, and we can be much faster. And in other methods, such as like modeling plasticity, this is a complex multi-scale phenomena. And we have solvers at different scales because it's too complicated to do all at once. And so the fine scale, we replace the traditional solver with the neural operator. And what we see is a big speed up here. And so that also shows, like in some of the more complex problems, the benefits we get from these methods is even larger. Another such example is carbon dioxide capture and mitigation. So, one of the hypotheses is that climate change will be so untenable that one of the solutions would be to actually capture carbon dioxide and store it deep underground, right? And so to see if this is feasible, we need to accurately model how will the gas saturate and the pressure builds up in this underground, and this is complex because this is a multi-phase flow, right? There are different phases here. And what we see again is a big speed up. And here what we did was we added like a residual layer, which did have like a unit along with the Fourier neural operator, which could capture both the fine and coarse scales effectively. And we see a big speed up over traditional methods. Another example is understanding the molecular dynamics of viruses. And this one, we did it on the COVID virus. And what we see is the ability to understand, right, like the different regions. Like the idea is like the conformal changes that happen in different parts of the COVID, is important for it to be able to replicate effectively. So understanding this is really important. Again, the details I won't have you here, but what it shows is the versatility of this method in being able to handle so many different time varying, high resolution spatial variations, and being able to get big speed ups over traditional methods. We also see the impact on transformer architectures, where we show that you can replace self-attention with a version of this Fourier neural operator. So effectively what it's doing is to enable token mixing much more effectively by making it as a continuous object rather than discrete. So it's making a continuous approximation. And through that, we see that we get the same quality as the full attention, but be much better in terms of the number of flops. And so that's also something we see with the clustering of the representation in these layers. And so this shows that there can be many diverse use cases for this methodology. And talking about scale, we are integrating all this into the NVIDIA SimNet, which will help us scale up on DGX and bigger systems and be able to solve highly complex real-world problems and incorporate both forward, inverse, data assimilation, all these aspects together. So as another example of what algorithmic development is needed for AI for science, I'll talk about computing the quantum mechanical energy of the molecules. And this is really important for drug discovery. Indeed, that involves so many complicated steps here. But the first part is, of course, the search. How do you search and come up with candidates of good molecules? And that space is enormous. It's 10 to the 60, right? So the question is, can we, come up with good search strategies, but also be able to accurately compute what is the right property prediction of these molecules. And to do that, what we did was to combine domain knowledge. So these molecular orbitals are calculations that are fixed, right? That say how much each atom has influence over others in the molecule. And so on top of this, we built the graph neural network to learn and predict the energy, right, in this molecule. And so the main reason why we use molecular orbitals is now this becomes transferable. So even if you trained only on small molecules like we did with just under 40 atoms, we can directly make this method work on much larger molecules, right? 10 times larger than what we've trained. And that's because these orbitals capture the dependencies within a molecule, irrespective of how big it is. So we can avoid the distributional shift between training and testing by incorporating this domain knowledge. And so we see that in the outcome here, that our method, right, has accuracy similar to these gold standard traditional methods, but be 3 orders of magnitude faster. So that's the benefit we get, that with AI, we can retain the accuracy while being 1,000 times faster. And this is possible because we combine domain knowledge with the flexibility of graph neural networks. And also compared to other machine learning methods, we are very efficient in terms of the data needed, right? Because remember, we need training data from these traditional methods. That's also very expensive. And so the lower amount of data we can use, the better, right? So, and that's where having the orbital information as domain knowledge helps us work with lower amounts of data. And so with this, we can now explore a broad range of properties, right? So I've just mentioned a few here that's important to chemists, geometry optimization being an important one. And compared to like, right, traditional methods, ours is much faster while also being more accurate. And you can see that here with the match. Recently, we also used this method to understand how the COVID virus, right, interacts in aerosols, right? I mean, this is so important because this is what makes it so infectious. And again, not a lot of details here, but the main aspect is that the ARPANET calculations can make it much more accurate in terms of the energy predictions compared to the standard methods, because the methods like DFT, which are the gold standard, are way too expensive to be run on molecules of this scale. Yeah, so to conclude here, I truly believe that AI for science is the future of science and also the future of AI, right? But we need to be thoughtful because so many times this needs extrapolation and zero-shot generalization, right? So it may not be your standard supervised learning method. We need to ask, is this testing going to be very different from the training data? And in case of partial differential equations, the reason was because we need the flexibility to operate on different resolutions and different grid sizes. And the other aspect we found with ARPANET is using the right amount of domain knowledge, right? That is cheap and quick to compute, and building graph neural network on top of it can greatly enhance its ability to transfer from small molecules directly to much larger molecules. Thank you.